Dear students, very good morning. Today we will discuss about root locus, why we are using root locus and how we can construct a root locus with the provided steps. First, we should know why we are using a root locus. In the previous classes, we discussed about the stability of a system by using a root array. In what way we can analyze the stability of the system. That means either the given system is stable or unstable or marginally stable. So here also we can be able to analyze the stability of the system, especially with respect to the parameter called gain. For this analysis, we are using root locus. Root locus is actually developed in the year of 1948. So in our root locus, we are going to make some graph. From the graphical or visualization analysis, we can able to see if you want to make a system in a stable variables, how we can make the changes, in what way we can make the changes in order to get a or achieve a stable system. So that's why we are using our root locus. If we want to construct a root locus, so many steps are there. We have to follow 6 to 8 steps with respect to the problem. So each and every step is consuming some time. So we need to deal the each and every step in a careful way. So today we will see one sample problem. Within a single hour we can't be able to complete the entire construction of this problem. So we will see few steps in one lecture, few steps in another lecture like that. We will complete that problem within 2 or 3 classes. So now here problem 1 is provided, that is the open loop transfer function of a control system is given by k divided by s into s square plus 4s plus 13. We need to construct the root locus for this open loop transfer function g of s. So the given system is a unity feedback system. So we know unity feedback system means we can assume h of s is equal to 1. Okay, now we will see how we can proceed. Sorry, sir. So here 8 steps are there. So step number 7 and 8 may be used for some problem, may not be used for some problem. That is, it depends upon the given problem or a given g of s value. So now we will see one by one. So step number 1 is we need to locate the poles and the zeros in the graph sheet. That is the location of poles and the zeros. So we need a normal graph sheet to construct a root locus. In that normal graph sheet, we need to locate the poles and zeros of the given problem. So we need to take the consider the open loop transfer function g of s. From this g of s, first we should identify the poles and the zeros. So already we know what I mean by the poles as well as zeros. So zeros means roots of numerator. So in this g of s expression, if roots of numerator, that means if any s is available in the numerator, then there may be a possibility of getting roots of numerator, that is called zeros. Similarly, roots of denominator is called zeros. So here we know in this g of s, so k only is available in the numerator. That means there is no zeros. Since there is no s parameter or s terms in the numerator, so there is no zeros. So simply we can write no zeros for this particular problem, right? Then we need to identify the poles. So poles means roots of s in the denominator. In the denominator, we have a expression s into s square plus 4s plus 13. We need to assume which is equal to 0. Now these roots of this particular equation is called poles. So we know first root is s equal to 0, so that we can write p1 equal to 0. So here three poles are possible since we have s into s square. If you are multiplying them, we will get s power 3. Sorry, so that this expression is having three roots. So three roots means three poles. Three roots means three poles. So first pole is s equal to 0, so that p1 equal to 0. We need to identify root number 2 and 3. Let us assume p2 equal to p3 equal to. We need to identify p2 and p3. So for this, this is the second order equation or quadratic equation. If we are multiplying any two numbers, we need to get 13. If we are adding those two numbers, we need to get 4. So we don't have any whole number combinations for that. So we have alternative options to find the roots of this particular one. The formula is minus b plus or minus square root of b square minus 4ac divided by 2a. Sorry. So here a equal to 1, that is coefficient of s square. Then b equal to 4, coefficient of s. C is constant 13. So we can substitute those values. B equal to 4. So minus 4 plus or minus square root of b square, that is 4 square minus 4 into a equal to 1, c equal to 13 divided by 2 into a. If we are simplifying this particular one, minus 4 plus or minus 16 minus 437, 41352 divided by 2. So we can rewrite minus 4 plus or minus, here 16 minus 52 is minus 36. So minus the square root of minus is j, square root of 36 is 6 divided by 2. So here 2 is common, we can write minus 2 plus 3j is first root. Similarly, minus 2 minus 3j is second root. So we can write p2 is minus 2 plus 3j, p3 is minus 2 minus 3j. Right, this is what p1, p2, p3. So for this problem, there is no zeros since the given g of s doesn't have any s parameter in the numerator. So the denominator is having s into s square plus 4s plus 30. So the roots of denominator is called poles. Since here we having s into s square, 3 poles are there. So first pole is very simple pole, p1 equal to 0. P2 and P3 is converse conjugating pole. So your step number 1 is location of poles and zeros. So in the graph sheet we need to mark these poles and zeros. Here we will try to draw a graph for this particular one. Let us assume we are having a normal graph sheet. In that normal graph sheet, we should make one reference line for x-axis, then one reference line for y-axis. So this axis is called a real axis or x-axis, and y-axis is called a imaginary axis. So this is a normal graph sheet. Then we should make the scaling for this particular one. Since there is no zeros, we don't care about the particular one. We have poles. In this pole, you can say P1 is 0, very simple one. P2 and P3 is having real part and imaginary part. Real part is minus 2, imaginary part is plus 3j minus 3j. So that in our normal graph sheet, we have lots of boxes, whole boxes. So we can take x-axis for scaling. I'm saying for x-axis, we can assume 1 centimeter equal to 0.5 unit. Similarly, in y-axis, 1 centimeter equal to 0.5. That means, let us assume, so this is called the x-axis or real axis. Here y-axis or imaginary axis. Yes, we will extend this graph. Yes. So we assumed x-axis 1 centimeter equal to 0.5, so that we can write 0.5, 1, 1.5, 2, 2.5. Here minus 0.5, minus 1, minus 1.5, minus 2, minus 2.5, minus 3. So y-axis is j, so again 0.5j, 1j, 1.5j, 2j, 2.5j, 3j. Here minus 0.5j, minus 1j, minus 1.5j, minus 2j, minus 2.5j, minus 3j. Yes. So this is for graph sheet. We are drawing roughly. If you are doing this graph in a real graph sheet, we will get a perfect graph. Right. So here now we need to locate your poles and zeros here. So we know we have 3 poles. Right. P1, P2, P3. Yes, let me mark them. So we needed to use small x symbol to represent pole. To represent pole, we need to use a x symbol. If we are having any zero, we should use some small circle to represent that one. So in this problem, we have only poles. So your first pole is, yes, we know P1 equal to 0. So this is what P1, that is equal to 0. P2 is minus 2 plus 3j. P2 is minus 2 plus 3j. P3 is minus 2 minus 3j. You can see here how we should mark that minus 2 plus 3j minus 2 minus 3j in the graph sheet means. So very simple. So P2 is minus 2 plus 3j. Minus 2 represents your real number. So we have 0.5, 1, 1.5, 2. So this is the point for minus 2. So here we have some line here, vertical line. Similarly, your imaginary part is plus 3j. So this is plus 3j. Meeting point out is minus 2 as well as plus 3. Is called P2, second pole, right? That is minus 2 plus 3j. Similarly, your third pole is minus 2, again minus 2, minus 3j. So we will have approximately here. Let us assume this is representing your P3. So this is about step number 1. We need to locate poles and zeros in the graph sheet. Right. So we have 3 poles, P1 equal to 0, yes, we marked here. P2 equal to minus 2 plus 3j. So this is minus 2 line plus 3j line. Meeting on them is called the minus 2 plus 3j. Similarly, P3 is minus 2 minus 3j. So step number 1 is over. Now step number 2. Again, step 2 is very simple. So before entering into step 2, we should know one information. If you are going to draw a root locus means the number of root locus is equal to number of poles. That is very important. Number of root locus branch. Number of root locus branch is equal to number of poles. So in this problem we have 3 poles, that means we should draw 3 root locus branches. Similarly, each and every root locus will start from pole ending at 0. Each and every root locus will start from pole and ending at 0. Now we will enter into step number 2. Step 2 is root locus on real axis. Root locus on real axis. So here concept is very simple. Real axis means we know x-axis is called a real axis. We need to identify the root locus on this particular real axis. How we should identify the root locus on a real axis means we should verify this x-axis from RHS to LHS. So from right hand side to left hand side we need to make some verifications on the real axis. How we are verifying means we need to identify is there any pole or zero is present on the particular real axis. So we need to verify the real axis from right hand side to left hand side. In what way is there any pole or zero is present on the real axis. If we are verifying, we can see from left hand side to right hand side if we are moving, we have P1 at the real axis. So P1 is a pole that is present at the real axis. If any pole is present at the real axis, we should stop the root locus from that point. We should stop the root locus from that point. So here we have P1 at the real axis. So I'm going to start the root locus from P1. That means we should draw the root locus from P1. Yes. So in your graph sheet, yes, we can draw a straight line also with a darker line. If you are doing any graph, we know all the reference line must be light color, only the required graph must be dark color. So here root locus is the required graph that must be dark color. So I am verifying the x-axis from right hand side to left hand side. I am having the first point P1 at 0. So we started the root locus at P1. We should draw the root locus towards the left hand side. Here I am drawing the root locus up to end of your graph sheet. Up to end of your graph sheet. Why? So just now I told in any problem the number of root locus branches is equal to number of poles. That is one point. Apart from that, each and every root locus will start from pole and ending at 0. Will start from pole and ending at 0. So in this particular problem, we are having 3 poles, but there is no 0. That means first root locus will start from P1, ending 0 at infinity. Second root locus will start from P2 and ending 0 at infinity. Similarly, third root locus will start from P3 and ending 0 at infinity. So here this first root locus is started at P1 and we are drawing through the left hand side. There is no other point, so this first root locus is ending at infinity. This is for this particular problem. For example, I am saying in some other problems, if we are having one pole, let us assume we are having Z1 equal to -3, then what will happen? This is for example only. I am saying this is not applicable for this particular problem. If we are having 1, 0, Z1 equal to -3, then what will happen? Here we are going to draw that Z1 equal to -3. If this is the case, step 1 is now location of poles and zeros. We located P1, P2, P3 as well as Z1 here. While doing the second step, that is root locus on real axis, we are going to verify the real axis from right hand side to the left hand side. So we are having the pole P1 first. We are starting that root locus from P1. We are drawing a root locus towards the left hand side. In the left hand side, here we are having the second point, right. We should stop the root locus on the second point or pole. After that, we should not draw any root locus. So your first root locus is started at P1, ended at Z1. We don't have any root locus here. That means That means what? We don't have any root locus here, only reference line is there. So this is the way we should do the step number 2. So here I am undoing the process. Since we don't have any zeros for this problem, yes, your original root locus is, we are getting that root locus up to end of the graph sheet. So for this problem, we should make 3 root locus branch. Out of 3 root locus, first root locus is over. This is our step number 2. Right. Sorry. Step 3. Here we need to find the angle of asymptotes and the centroid. In step number 3, we need to find the angle of asymptotes and centroid. So both are formula based on. So we have formula for those two things. Okay, this is step number 3. First, we should write the formula for angle of asymptotes. Angle of asymptotes is equal to plus or minus 180 degree into 2q plus 1 divided by n minus m. So here n is number of poles. So q equal to 0, 1, 2, up to n minus 1. N is number of poles. M is number of zeros. So we know in this problem we have 3 poles. So number of poles equal to 3. There is no 0. So number of zeros equal to 0. Since n equal to 3, we should proceed up to n minus 1 means 3 minus 1 equal to 2. So we need to identify angle of asymptotes at q equal to 0, at q equal to 1 and at q equal to 2. Now let us assume q equal to 0. Here angle of asymptotes is equal to, if you are substituting q equal to 0 in this formula, we will get 180, that is plus or minus 180 into q equal to 0 means 2q becomes 0, so into 1 divided by n equal to 3, n equal to 0, so 3 minus 0, so equal to plus or minus 180 divided by 3 equal to plus or minus 60 degree. So this is our first angle of asymptote at q equal to 2. If q equal to 1, then angle of asymptotes is equal to plus or minus 180 into, if you are substituting q equal to 1, that becomes 3 divided by 3. So we can cancel 3 into 3, which is equal to plus or minus 60 degree. Then if q equal to 2, then angle of asymptotes equal to plus or minus 180 into 5. So 2 into 2, 4 plus 1, 5 divided by 3, which is equal to plus or minus, we can cancel 3 with 180 means 60, 60 into 5, 300 degree. So we can write minus or plus 60 degree. That means plus 300 equal to minus 60, minus 300 equal to plus 60. Why we are saying like this? So if we are considering a complete circle, we know, so this is 0, this is plus or minus 180, here 90, here 270. This is positive angle. If you are considering negative angle, minus 270, minus 180, minus 90. Here if you are considering this particular point, this is actually 60 degree in positive. minus 300 degree in negative. Similarly, if you are considering this particular point, this is 300 degree in positive minus 60 degree in negative. So that we are writing here. So this is about angle of asymptotes. So we have 3 angle of asymptotes, so those things are over. So next one is a centroid. Centroid equal to sum of poles minus sum of zeros divided by n minus m. Here n is number of poles, m is number of zeros. In numerator we are having sum of poles and sum of zeros. So we have 3 poles, so P1 plus P2 plus P3 minus, there is no 0, so 0 divided by n equal to 3, m equal to 0. Now if you are substituting P1, P2, P3, P1 equal to 0, P2 is minus 2 plus 3j, P3 is minus 2 minus 3j divided by 3. We can cancel plus 3j and minus 3j, so which is equal to minus 4 by 3, which is equal to minus 1.33. So centroid equal to minus 1.33. Angle of asymptotes is plus or minus 60, minus or plus 60, both are same. So 60 degree plus 60 minus 60, then plus or minus 180. Yes, we have some mistakes here. Sorry. So here, yes, this 3 and 3 cancel. Here we are having 180 degree. Yes. Now we will see how we should mark the centroid and angle of asymptotes in our graph sheet. In the locus, yes, let us assume we will take this graph sheet again. Here we need to mark the angle of asymptotes and the centroid. First we should mark the centroid, right? So centroid is minus 1.33, we can calculate approximately, yes, we will have centroid here. Then from the centroid we should mark plus or minus 180 degree as well as plus or minus 60 degree. For plus or minus 180 degree, there is no necessity to mark any point like that, since already we have a reference line for 0 and 180 degree. Right, already we are having reference line for 0 degree and plus or minus 180 degree reference line. So this is the same line is for angle of asymptotes also. There is no necessity to redraw that 180 degree reference line. We should mark that plus or minus 60. So for that, the concept is very simple. So we should mark that plus or minus 60 degree from the centroid. So if you are having protector, from the protector we can measure the 60 plus 60 from 0 to from here to here. Approximately we will have here. Sorry. We need to take this particular one in a dashed line format. So that I am taking this dashed line. So let us assume. Let us assume this is representing your plus 60 degree. Similarly, this is representing your minus 60 degree. Right. So this is representing plus 60 degree. This is representing minus 60 degree. So step number 3 is over. We mark the centroid area. From the centroid, we draw the line for angle of asymptotes of plus 60 degree and minus 60 degree. Then we will make some corrections in here. Wait a minute. Yes, again I'm going for shapes. Yes, we will have around third line. Yes. Yes, now it is okay. So this is plus 60 degree. This is minus 60 degree. So this is our step number 3. So we find out the centroid and the angle of asymptotes, and we mark the centroid area. Also we mark the angle of asymptotes from the centroid plus 60 degree and minus 60 degree. That plus or minus 180 degree angle of asymptotes is not necessary to draw here, since already we have one reference line on that. Now we will move into step number 4. Step number 4 is to find and breakaway and the breaking point. So step 4, we need to find breakaway and the breaking point. Break away and the break in points. So here we need to follow some lengthier step, but steps are very easy one. To find the breakaway and the breaking point, we need the characteristic equation of the given problem or given system. So characteristic equation means first we need to identify the closed loop transfer function. From the closed loop transfer function only we can able to find out the characteristic equation. So we know closed loop transfer function is mentioned by C of S divided by R of S, which is equal to G of S divided by 1 plus G of S into H of S. Yes, we know this formula from unit number 1 onwards we are discussing about it. Here H of S is feedback, that is unity feedback system, so H of S equal to 1. G of S is provided already, so I am rewriting that G of S here, K divided by S into S square plus 4S plus 13. So if I am substituting that G of S here, we are having K divided by S into S square plus 4S plus 13 in the numerator divided by 1 plus again K divided by S into S square plus 4S plus 13. How we can simplify? In the numerator we have K divided by 1 term. In denominator we have 1 plus K divided by 1 term. Let us assume if we are having a term like x by y divided by 1 plus x by y, so we can simplify x by y divided by y plus x divided by y. We can cancel y with y, then we can write x divided by x plus y or y plus x. So if you are comparing these equations with the given expression, x equal to k, y equal to s into s square plus 4s plus 13, so we can write x, that is k, divided by, in denominator we need to add both the terms, so I can write s into s square plus 4s plus 13 plus k. So this is a simplified version of this closed loop transfer function. Now we know characteristic equation means we should equate the denominator of the closed loop transfer function equal to 0. So here denominator is, therefore the characteristic equation is s into s square plus 4s plus 13 plus k, which is equal to 0. So if you are multiplying this s within the bracket, s cube 4s square 13s plus k equal to 0. So to find the breakaway and the breaking point, first we need to identify the characteristic equation from the given open loop transfer function. Then we should find out the expression for k. So k equal to, if you are moving the remaining terms in the RHS, minus of s cube plus 4s square plus 13s. Then we should find out dk by ds. That means we should differentiate this k with respect to s for 1 time. So we will get minus of differentiation of s cube. S cube is 3s square. Then 2 into 4 into 2, 8s plus 13. So this is a dk by ds. Then we should assume dk by ds equal to 0. Assume dk by ds equal to 0. That means we can write this expressions like, therefore minus of 3s square 8s plus 13 equal to 0. Since in the right hand side we have 0, so we can write 3s square plus 8s plus 13 equal to 0. We can cancel this minus. Now we need to identify roots of this particular equation. We need to identify roots of this particular equation. Here is expression is started with s square, so 2 roots are possible. But we know this expression is doesn't have any whole number, partial numbers. So we can't write like that. So we should go for the basic equations which is used to identify the roots of a quadratic equation. That formula is minus b plus or minus square root of b square minus 4ac divided by 2a. The same formula which we used to identify the poles. This is g of s. Here we can see a equal to 3, b equal to 8, c equal to 13. So a equal to 3, b equal to 8, c equal to 13. So we can rewrite like minus 8 plus or minus square root of 8 square is 64 minus 4 into 3 into c is 13 divided by 2 into 3. We can rewrite minus 8 plus or minus square root of 64, 4 into 3 12, 12 into 13 minus 156 divided by 6. So we can rewrite it again, plus or minus 8, minus 8 plus or minus 64 minus 156 means we will have square root of minus 92 divided by 6. So we can write minus 8 plus or minus, if you are taking a square root for 92, we will have 9 point something. Wait a minute, I will identify the exact value. So square root of 92 is 9.59. Why we are using j here means we are having minus in the square root divided by 6. So we can write minus 8 by 6. Minus 8 by 6 means minus 1.33 plus or minus the 9.59 divided by 8 means we will have So 9.59 divided by 6, 1.59 G. So we can write your first root is minus 1.33 plus 1.59 G. Second root is minus 1.33 minus 1.59 G. So we can write the roots of dk/d is equal to 0 is s1 equal to minus 1.33 plus 1.59 G. s2 is minus 1.33 minus 1.59 G. Now, what is the condition for breakaway and breaking point means? From the characteristic equation, we are finding the roots of dk/ds. If the roots of dk/ds is real and positive, then those roots are breakaway or breaking points. Otherwise, there is no breakaway and breaking point. So, the roots of dk/ds is positive and real means we can say those roots are maybe a breakaway or a breaking point. Otherwise, there is no breakaway or breaking point. Here we can see both the roots are having negative number. That means there is no real number. Also, they are having complex conjugate value, J value. So, the roots of dk/ds is not a real and positive number. Therefore, there is no breakaway and breaking point. So, we can conclude this step as here the roots of dk/ds is not a real and positive. Therefore, there is no breakaway and breaking points. So this is the conclusion of the step number 4. Right. Now we will continue with the step number 5. So up to now, in step number 1, we find out the codes and zeros and mark them in the normal graph sheet. In step number 2, we found the root locus on real axis. In step number 3, we find the angle of departure and the centroid, and we mark the centroid. From the centroid, we mark the dashed line for the angle of asymptotes, plus or minus 60 and plus or minus 180. Then in step number 4, we find out is there any breakaway or breaking point. Since the roots of dk/ds is a negative number as well as complex conjugate number, we conclude that there is no breakaway as well as breaking point. Now in step number 5, we are going to find out the angle of departure. Actually, step number 5 is common for angle of departure as well as angle of arrival. So when we need to find the angle of departure means if your open loop transfer function g of s is having complex conjugate poles, then we need to identify angle of departure. If your g of s is having complex conjugate zeros, then we need to identify angle of arrival. Since we know each and every root locus branch starts from pole, so that if you are getting complex conjugate pole, we need to identify the releasing angle of departure. Similarly, each and every root locus is going to end at 0, so that we are identifying angle of arrival, angle of entry at the 0. So in this problem, we are getting two complex conjugate pole. So just I am simply drawing on this graph here. This is with P1. Here we are getting P2 Here we are having P3. So in P2 and P3 is complex conjugate poles. So we need to identify angle of departure at P2 as well as angle of departure at P3. Since both are same magnitude and they are having sign changes in the imaginary part, that means P2 equal to minus 2 plus 3j and P3 equal to minus 2 minus 3j. They are having same magnitude and only changes in the imaginary part sign. If we are finding the angle of departure at P2, that is more than sufficient. If we are changing the sign of angle of departure at P2, which is equal to angle of departure of P3. Now we are going to find the angle of departure at P2. So this is very simple. We have a formula from this: 180 degree minus sum of angles of vectors from other poles to the complex pole P2. This is second term. 180 minus sum of angles of vectors from other poles to the complex pole P2 plus same statement sum of angles of vectors from zeros to the complex pole P2. So this is the formula to find angle of departure at P2. So 180 number no issue. What is the meaning of second term? Sum of angles of vectors from other poles to the complex pole P2. That means we are going to find out angle of departure at P2. We are going to find out angles of vectors at P2. So we need to identify the angles from other poles to the P pole, other P2. Other poles means P1 is one other pole, P3 is one other pole. So we need to determine the angle between P1 and P2, P3 and P2. We need to add them. That is the actual meaning of the second term. How we are going to add? So here, let us assume we have some dashed line. So this angle is representing angle between P1 with P2. Let us assume theta 1, that is. Then similarly we are connecting P2 with P3. Let us assume this is the angle between P3 and P2. Now we are connecting P1 with P2, P3 with P2. So second type is sum of angles of vectors from other poles to the complex pole P2. First other pole is P1. So the angle between P1 with P2 is theta 1. Similarly, the second other pole is P3. The angle between P3 and P2 is theta 2. Then what about the third term, sum of angles of vectors from zeros to the complex pole P2? Here there is no zeros in this particular problem, so your third term becomes 0. Suppose if you are having one 0 here, let us assume we are having Z1 here means we should connect this one. Let us assume this is theta 3. This theta 3 will become in the third term here. But in this problem, we doesn't have anything like that. So there is no necessity for making that 0. So we can rewrite this formula with the given value, which is equal to 180 degree minus sum of angles of vectors from other pole to the complex pole P2 means angle between P1 and P2 is theta 1, angle between P3 3 and the P2 is theta 2, then there is no 0, so that we are adding 0. Now we should measure by using your protector. We can measure what is the phase angle of theta 1. Similarly, we can measure what is the phase angle of theta 2. Here theta 2 is right angle, so 90 degree. For theta 1, we can measure using protector. So here theta 1 is 123.7, theta 2 is 90 degree. If you are simplifying this one, so 123.7 plus 90 equal to 213.7. So 213.7 minus 180 means we will have minus 33.3 degree. This 33.3 degree is the 33.3 is the angle of departure at P2. So similarly, we can write angle of departure at P3. Angle of departure so angle of departure at P3, which is equal to similar magnitude of angle of departure at P2 with it changing the sign, that means plus 33.3 degree. Now that is over. Now what we should do? So we should mark this angle of departure in our graph sheet. So already we have the graph. I am going to take that graph. Yes, this is our graph. Here we know the angle of departure at P2 is minus angle of departure at P2 is minus 33.3. So from P2, wait a minute. Yes, we should mark a dot line. Yes, wait a minute. I will reduce the thickness. Yes, now it is okay. So angle of departure at P2 is minus 33.3. Similarly, angle of departure at P2 is plus 33.3. Just to draw a dashed line from here, that is more than sufficient. So we can write this phase angle is 33.3 degree. This is minus 33.3 degree. Now step number 5 is over. We marked those phase angles here. Now we should enter into step number 6. So step number 6 is the last step for this problem. So for this problem, 3 poles are there. We need to identify 3 root locus branch. Out of 3 root locus branch, first root locus branch is over from P1 to infinity. So second root locus is going to start from P2. That root locus is going to releasing at an angle of minus 33.3. Then that root locus is going to travel in parallel with this plus 60 degree angle of asymptotes. Similarly, your third root locus is going to start from P3 and going to releasing at an angle of plus 33.3 degree and in travel in parallel with this minus 60 degree angle of asymptotes. Now only missing point is we need to identify the crossing point on imaginary axis. So for that we are entering into step number 6. Sorry. In step number 6, we needed the characteristic equations of the given system. So already in step number 4, we find what is the characteristic equation of the given system. So from that we can proceed. Go to step number 6. So step 6 is to find crossing point on imaginary axis. So step number 6 is crossing point on imaginary axis. So this is very simple step. In earlier subjects we may studied about this one. Just to rewrite that characteristic equation. I am going to rewrite that characteristic equation, which is s cube plus 4s square plus 13s plus k equal to 0, which is available in step number 4. Now we know s equal to j omega. Just substitute it here. S equal to j into omega. If we are substituting this s equal to j omega, we will get j omega whole cube 4 into j omega whole square 13 into j omega plus k, which is equal to 0. Right? Now, if you are simplifying j omega whole cube, j cube means j square into j square is minus 1, so we can write minus j into omega cube. J square is minus 1, so minus 4 omega square 13 j omega plus k equal to 0. Now we can separate imaginary term and real term. In imaginary term, we are having 13 omega 13 omega minus omega cube into j. So this is representing minus j omega cube plus 13 j omega, then plus k minus 4 omega square, which is equal to 0. Here we know this is imaginary part, this is a real part. So this 13 minus omega cube is imaginary part. Sorry, 13 omega into omega cube is imaginary part. K minus 4 omega square is real part. We know if we are having the expression like this, we can individually or separately equate them equal to 0. If we are equating imaginary part equal to 0, we will have 13 omega minus omega cube is equal to 0. If we are taking omega outside, 13 minus omega square equal to 0. Since in the RHS 0 is available, we can cancel this omega. Simply we can write, if you are moving this omega square into RHS, we can write omega square equal to 13. Therefore, omega equal to square root of 13. So which is equal to plus or minus 3.6. Since s equal to j omega, we can write j into omega equal to plus or minus 3.6 j. So this is the crossing point on imaginary axis. In plus 3.6 as well as minus 3.6. Similarly, if you are equating real part equal to 0, then what will happen? This is one side. If we are equating real part equal to 0, we will have k minus 4 omega square is equal to 0. Therefore, we can write k equal to 4 into omega square. We know omega square equal to 13. In the previous step we have. Therefore, we can conclude k equal to 52. K equal to 52. Yes, now we are moving into our graph sheet with the concept of crossing point of imaginary axis plus or minus 3.6 j. Yes, so here we are having our graph. So crossing point on imaginary axis is plus 3.6. So here plus 3.6j, that is one crossing point, minus 3.6j is the second crossing point. Now we should draw our graph sheet. Yes, now we can see our second root locus is going to start from P2, then releasing at an angle of minus 33.3, then crossing through that plus 3.6j and travel in parallel with this particular 60-degree angle of asymptotes. Similarly, our third root locus starts from P3, releasing at an angle of plus 33.3, crossing at minus 3.6, and travel in parallel with this 60-degree angle of asymptotes. So that's all. So this is our second and the third root locus. Now we are having first root locus from P1 to end of our graph sheet, second root locus from P2 to end of our graph sheet, third root locus from P3 to end of our graph sheet. So this is the exact root locus of the given problem. So this six steps are more than sufficient to complete this particular problem. So up to this, your problem is completed. So just from this graph itself, I explained what are the steps we followed. In first step, we find out the poles and zeros from the graph sheet. Then we mark the poles and zeros in this graph sheet. So we are using cross symbol to represent a pole and a small circle to represent 0. So in this problem, three poles are available: P1 equal to 0, P2 equal to minus 2 plus 3j, and P3 equal to minus 3, minus 2 minus 3j. Then step number 2 is root locus on the real axis. For this, we are verifying the real axis from right hand side to the left hand side. If we are facing any first point, pole means we should start at a root locus from the pole. Yes, we are starting at a root locus from P1. Then draw the root locus towards the left hand side. If there any second point, we should stop it. Otherwise, we can draw the root locus up to end of our graph sheet. Then step number 3 is angle of asymptote and the centroid. So we use some formulas. From that formula, we found that centroid equal to minus 1.33 for this problem. Then angle of asymptote is equal to plus or minus 60 and then plus or minus 180. So for plus or minus 180, already we have our reference line on the plus or minus 180. So there is no necessity to redraw that particular one. So that I am drawing plus 60 degree and minus 60 degree angle of asymptotes from the centroid. Then step number 4 is to find the breakaway and the breaking point. So we have some steps. We need to identify the characteristic equation. From the characteristic equation, we should find out the formula for k, then dk by ds. Then we need to identify roots of dk by ds. If the roots of dk by ds is real and positive, then those roots will be considered as a breakaway and a breaking point. Otherwise, there is no breakaway and a breaking point. For this particular problem, the roots of dk by ds is having negative number as well as imaginary part. So there is no breakaway and a breaking point. Step number 5 is angle of departure and angle of arrival. If we are having complex conjugate pole, then we need to identify angle of departure. If we are having complex conjugate zeros, we need to identify angle of arrival. Here we are having complex conjugate pole P2 and P3. So we have some formula. From that formula, we found what is the angle of departure at the P2 and P3. Then we found some dash and reference line from P2 as well as P3 for the respective angle of departure. Then step number 6 is crossing point on imaginary axis. For this, we need to take the characteristic equation again, substitute S equal to J omega. then separate imaginary term as well as real term. From the imaginary term, we found crossing point when imaginary x is equal to plus 3.6 and minus 3.6. Yes, we marked that plus 3.6 and minus 3.6. Then we are drawing the second and third root locus. Second root locus starts from P2, releasing at an angle of minus 33.3, traveling to plus 3.6, as well as in parallel with this 60-degree angle of asymptote. Similarly, third root locus starts from P3, releasing at an angle of plus 33.3 degree, then crossing through minus 3.6, then travel in parallel with a minus 60-degree angle of asymptotes. So with this, the one problem on this root locus is completed. Just to go through these sessions one or two times, you can get some clear idea. So thank you for listening. Thank you.